Welcome to a video on section 4.5 regarding the linearization of functions. During this video, we'll be using the calculator a couple of times for some exploration, so you might want to grab a graphing calculator while you're watching this video and taking notes on it. So what is linearization of functions, or in this case, local linearity? Well, as the name implies, linear is something that looks like a straight line. And you'll kind of get an idea as to why this is specifically called local linearity as we go through this first exploration. First thing we'll do, however, is we'll graph y equals x cubed minus 3x in our calculator. So here I have my trusty app, the Wabbit. If I go to y equals, I'm going to clear all this junk I have here because I don't care to see it. So again, get your calculator out, go to y equals, and we're going to type in x cubed minus 3x. Now before I hit graph, I'm going to hit zoom and select option 4, which is z decimal. There's a good reason why I want to use zoom 4, and you'll see or understand that reason in about a couple minutes. Now the next thing I want to do is I want to find dy over dx, or the derivative, at 1 comma negative 2. The nice thing about these calculators is that you can actually find the value of a derivative for a graph. So if I hit second trace, which is a calc feature, and option 6, which is dy dx, and if I type in x equals 1, you'll see that we do get the value for the derivative, which is 1e negative 6. Well, y prime at x equals 1 is 1e negative 6, which is basically 0. The calculator, remember, does an approximation when it does a numerical derivative. We call it the symmetric difference quotient. I'm not sure if you remember that from last semester. So it's not going to say 0 exactly, but it'll say 1e negative 6, so it's close enough. So that means that the slope of the tangent at 1 negative 2 for our equation x cubed minus 3x is 0. That means that the equation of the tangent line at 1 comma negative 2 is going to be y equals negative 2. Because the slope is 0, we expect there to be a horizontal line that touches the point 1, negative 2. And if it's a horizontal line, it's going to be y equals negative 2, because that's the y coordinate of our point of tangency. So let's go back to our calculator here. Let's go to y equals, and let's type in y equals negative 2 and graph that. So again, the tangent line is y equals negative 2. We see it touching the point at 1 comma negative 2, so all is good. Now, why are we doing all this? Now, if you look at the instructions, we're going to take our cursor, move to the point 1, negative 2, either by tracing or using the calc value command. We'll just trace. It's a lot easier that way. And then we're going to zoom in 5 or 6 times. So I've hit the trace button, and let's move to 1, negative 2. Now, one thing you might notice is that as I'm moving along this curve, the x-coordinate's going up by 0.1 or down by 0.1. That's part of the zoom 4 or the z decimal feature. It allows us to kind of pinpoint where we want to go on our graph. So 1, negative 2, which is great. I'm going to zoom, option 2, and I'm going to hit enter. So see how it's zoomed in on the graph for us. And we're still at 1, negative 2. We see the curve, so it's just a bit more zoomed in. What if I enter again? So now we're zooming in even more. Let's hit it again. Now you start noticing the graph starts becoming more flat or a bit more horizontal. Let's hit it again. So now the 4th time I've zoomed in, and the graph definitely looks horizontal. It's almost like it's coinciding with our horizontal tangent line, y equals negative 2. Let's do it again. So I've done it a 5th time. Okay, they're almost identical. We'll do one more time for good measure. So now I've zoomed in 6 times. The graph y equals x cubed minus 3x and the horizontal tangent line are virtually the same. So let's go back to the notes. So what does the graph look like? A horizontal line. And what can you see about the curve and its tangent line if you zoom in repeatedly? That they're the same. So that's what's meant by local linearity, is that any graph, or I should rephrase that, any differentiable function, when you zoom in close enough, it's almost like it has a linear behavior to it. And if you were to draw a tangent line to that particular point, you would see that the tangent line and the curve would eventually coincide. So every differential function has something we call local linearity. So if a function is differentiable x equals a, it will be locally linear there. Or in other words, if you zoom in enough, the curve will look like a straight line, though it may not necessarily be a horizontal line. Let's explore this a bit more with our second exploration. So here we have f of x is the absolute of x plus 1, g of x is square of x squared plus 0.0001 plus 0.99. Now, if you were to plug in, say, for example, 0 for x, I think both y values would be 1. And it's almost like they're going to be kind of like the same equation, but let's work this out and see what happens. So I'm going to y equals, I'm going to do the absolute value of x plus 1. Absolute value, you could find by doing alpha window. Let's clear the other one. Square root x squared plus 0.0001 plus 0.99. Okay. Let's go to zoom 4 again. So here we have an absolute value function. Okay, so right now, I don't really see anything drastically different. They look like they're about the same. Oh, and actually, you know what? I forgot to make this a thick line for g of x. To make that a thick line, if you go to the left and hit enter a few times, okay, actually I had it, I missed it. There we go. Okay, so we have that. Okay, again, they're still virtually the same, but we could see how there's a change made with the second graph. Well, not a change, but we see the second graph appearing. So what happens is that g of 0 is 1. Also for our values of x that are big, compared to 0.001, root x squared, we know is absolute of x plus 0.99. So g passed through 0, 1 is very close to f. So again, if you were to plug in 0 into g of x and work it out, you would get 1. And essentially, it's kind of the same thing as absolute of x plus 1. So they're very close to each other. But here's the difference, is that f is never going to flatten out. G will. So, and here's the thing, absolute of x plus 1, hopefully you guys know, is not differentiable, right, because of the sharp corner. But g of x is actually going to be a differentiable function. It's just a square root function, right? So let's actually go back to our graph. Let's trace. We're at 0, 1. Let's zoom in. Okay. Zoom in a bit more. So here's the absolute value. There's this square root function. Zoom in again. So notice how the square root function starts becoming a bit more curved, which is how it should be, right? Because that has local linearity. And of course, it's eventually going to flatten out if I keep going. And again, the absolute value function will never flatten. If it's not differentiable, it's not going to have local linearity. Only differential functions have local linearity. So I think you get the point. So that's the exploration there. So what do you notice, again, is that f will never flatten out, g will. So f of x is not differentiable, g of x is differentiable. That's why you see that difference. So an important application about local linearity. If a function is differentiable at a certain point, it will be locally linear there. Thus, we find it reasonable and useful to approximate the y values of a function using the corresponding y values of its tangent line for values of x that are close to a. So the basic idea here is that the y values on the tangent line will approximately equal to the corresponding y values on the curve. And that's because, and this is for values of x near x equals a, where again, x equals a is going to be a point of tangency. So you have a comma f of a, you have a tangent line. When you're really close to x equals a, the y values on the tangent line are pretty much going to be the same as the y values on the curve, because they're going to be, again, locally linear. So let's take another look at this. So again, the equation of tangent to the differential function f of x at the point a comma f of a, we have right here. So our point is that the slope of the tangent line will be obviously the derivative at x equals a. And we know that y minus y1 equals m times x minus x, and let's say you find the equation of a line. Well, if your slope is your derivative, and we're calling x1 a, we're calling y1 f of a. If I rearrange things a bit, I should get this. F of a plus f prime of a times x minus a. And so that right there gives rise to an approximation for our function. So we use the notation L of x for this tangent line function. So L stands for linearization, or linear approximation function. So we use the notation L of x for this tangent line function when we use it as an approximation. So what this does, this allows us to approximate what a certain y value would be for our graph if we assume a linear approximation. So we, again, are assuming that our graphs are taking on some sort of linear behavior. We say that we are linearizing the function at x equals a, and x equals a is the center of linearization. And really, again, it's just like having a y-intercept, a slope, and x minus a. So we're just using all the stuff we've learned about linear functions before and just applying it to differentiable functions. Okay, so, and remember though, it's just a fancy name for the equation of the tangent line at x equals a, solve for y. That's really what this really is. So let's look at one example, and then we'll end the video. So you're asked to find the linearization of the following function x equals 16, then use to find an approximation for the fourth root of 17. Okay, so for part A, f of 16 is easy, right? There's going to be the fourth root of 16, which is just 2. But the fourth root of 17 is not so easy. But what if I called my function the fourth root of x, and I took the derivative? And remember, the fourth root of x is x to the 1/4 power. So if I take the derivative, it's 1/4 times x and negative 3/4. F prime of 16 is 1/4, 16 raised to 3/4 power. So I get 1/4 times 8, I get 1/32. So what I'm doing is I'm trying to find this function. L of x is f prime of a, sorry, f of a plus f prime of a times x minus a. So f of a I know is going to be 2, because that's, f of 16. My derivative is 1 over 32, x minus 16. So that's the linearization of fx equals 4 through 16 and x equals 16. Because we got our point, which is 16 comma 2, and our slope, which is going to be 1 over 32. Now, to find the 4 through 17, I can just use the approximation. L17 will be 2 plus 1 over 32 times 17 minus 16 will be 2 plus 1 over 32. So 2 and 1 over 32. So the beauty about linearization is that it allows us to approximate something kind of weird, like the 4 through 17. Like if you ask me what the 4 through 17 is out of the blue, I don't know. But I can use the calculator. If I did 17 raised to the 1/4 power, okay, but 2 plus 1 over 32 is going to be a pretty decent approximation. So that's the beauty about linear approximation, is that we're choosing an x value, 17, that's close to 16, and assuming linear behavior, and we can approximate it. Now, for part B, use the concavity of fx on the open interval from 16 to 17 to predict whether your answer in part A is too big or too small. Well, going back to the calculator, the real value is 2.0305. The approximation is 2.03125. Clearly, our approximation is too big. But how do I prove it? Using concavity. Well, if I take the second derivative, you should get negative 3/16 times x and negative 7/4. And clean it up a bit. Negative 3/16 times the 4th root of x raised to the 7th power. Now, if you do plug in anything between 16 and 17 in this interval, your second derivative is going to be negative. The 4th root of, like, say, 16.5 is positive, but you still have that negative 3 up top. So what's going to happen is that our curve is going to be kind of like this. It's going to be concave down in an interval from 16 to 17. And our tangent line, which was this right here, that's actually a tangent line too, if you think about it. Is like that. So if that's at 16, then at 17 it's going to be probably right there. So we can see why that approximation should be too big compared to the real thing, if we try to visualize it. So that takes care of this video. We will talk about this again in class, and we'll also do the rest of the examples together as a class. All right, have a great day. See you later.